Welcome. Let's talk about the sun. Our sun. The star that makes everything possible. Despite the fact that there are billions upon billions of stars scattered throughout the universe, twinkling in the darkness of space, the sun is the only one in our solar system. It stands alone at the center of our cosmic neighborhood, the singular source of light and warmth for everything we know. Just one star, but what a star it is. This magnificent ball of light has been burning for approximately 4.603 billion years. Think about that for a moment. 4.5 billion years. Long before the first human ever looked up at the sky. Long before the dinosaurs walked the earth. Long before Earth itself had cooled enough to form oceans. The sun was already there, shining steadily, patiently, waiting for the story of our planet to unfold. Scientists classify our sun as a G-type main sequence star, with the technical designation G2V. You might hear it called a yellow dwarf, though that name is a bit misleading. It's not particularly small, and it's not really yellow when you see it from space. But the name has stuck, and it helps us understand where our sun fits in the grand catalog of stars that populate the universe. Now, when we talk about the sun's dominance in our solar system, the numbers are almost hard to believe. The sun holds 99.86% of all the mass in our entire solar system. Let that sink in for a moment. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust and gas floating in the space between worlds, all of that combined makes up less than 1% of the total mass. The sun is, quite literally, almost everything. How much does the sun actually weigh? Well, it tips the cosmic scales at approximately 1.989 times 10 to the 30th power kilograms. That's a number so large it's difficult for our minds to grasp. To put it in perspective, the sun weighs about 333,000 times as much as Earth. If you could somehow place Earth on one side of an enormous balance scale and wanted to balance it with solar material on the other side, you'd need to add 333,000 Earths worth of the sun's mass before the scale would even begin to tip. The sheer size of the sun is equally staggering. In terms of volume, you could fit roughly 1.3 million Earths inside the sun. Imagine that. Over 1 million planets the size of ours, all nestled inside that glowing sphere we see in our daytime sky. When we measure the sun's diameter, we find that it's 109 times wider than Earth. If Earth were the size of a marble, the sun would be a sphere nearly as tall as a person. Interestingly, the sun is the closest thing to a perfect sphere found in nature. Of course, nothing in the universe is absolutely perfect, but the sun comes remarkably close. Its difference between its polar and equatorial diameters is just 10 kilometers out of its nearly 1.4 million kilometer diameter. That's an astonishingly small variation, making it more spherical than most balls you could hold in your hand. Here's something that surprises many people. The sun has no solid surface. If you were somehow able to travel to the sun and tried to land on it, you wouldn't find ground beneath you. Instead, you'd simply fall through increasingly dense layers of plasma, sinking deeper and deeper into ever more extreme temperatures and pressures. There's no there in a sense. No place to stand. No surface to touch. That's because the sun exists in a state of matter called plasma. Most of us learn about 3 states of matter in school: solid, liquid, and gas. But there's a 4th state, and it's actually the most common state of matter in the universe: plasma. In this state, the temperature is so incredibly high that electrons are stripped away from their atoms, creating a soup of charged particles that behaves in fascinating ways, responding to magnetic fields and electrical currents in ways that ordinary gas cannot. What is the sun made of? Well, by mass, it's roughly 73% hydrogen, 25% helium, and about 2% heavier elements. Hydrogen is the simplest element, just 1 proton and 1 electron. Helium is next with 2 protons. These light elements make up the vast majority of the sun's composition. If we count by atoms rather than by mass, the numbers shift slightly. By atom count, the sun is 91% hydrogen and 8.9% helium. Everything else, all the other elements on the periodic table, make up less than 1%. And here's a fascinating detail. There's gold in the sun, actual gold. Not very much, of course, but it's there. Small amounts of gold atoms exist inside the sun, and they weren't created by the sun itself. Instead, they were created by previous supernovas, the catastrophic explosions of massive stars that died long before our sun was born. Those ancient stellar explosions forged heavy elements like gold, scattering them into space, and eventually some of that enriched material came together to form our sun. This tells us something important about the sun's place in the cosmic timeline. It's what astronomers call a population 1 star. That means it's a relatively young star, at least in cosmic terms, formed from material that was already enriched with heavy elements from earlier generations of stars. The very first stars in the universe were made of almost pure hydrogen and helium. They lived, they died, and they seeded space with heavier elements. Our sun is built from that legacy, a descendant of stars that came before, carrying within it the chemical heritage of the ancient universe. So there we have it, the sun, our one and only star, ancient beyond our everyday comprehension, massive beyond our intuitive understanding, made of the simplest elements and yet carrying traces of cosmic history written in gold. It is the center around which our world turns, the source of our daylight, the reason we are here at all. Let's journey inward now to the very heart of the sun. To understand what makes our star shine, we need to travel deep inside, to a place where the conditions are so extreme they're almost beyond imagination. At the center of the sun lies the core. This is the innermost 25% of the sun's radius, and it's where all the action happens. Everything that makes the sun a star, everything that allows it to shine and warm our world, begins here in this central furnace. The pressure in the core is almost impossible to comprehend. It reaches 260 billion times Earth's atmospheric pressure at sea level. Think about that for a moment. The weight of our entire atmosphere pressing down on us, multiplied by 260 billion. It's a crushing, immense force that squeezes matter together in ways we never experience in our everyday lives. Under this enormous pressure, the matter in the core becomes incredibly dense. The core is 150 times denser than water. Even though it's made of plasma, of hydrogen and helium in that exotic fourth state of matter, the sheer pressure compacts it until it's far denser than any solid or liquid we're familiar with here on Earth. And the temperature. The temperature at the core reaches 15 million degrees Celsius. 15 million degrees. At such temperatures, matter behaves in ways that would seem like pure magic if we didn't understand the physics behind it. Atoms are moving at tremendous speeds, colliding with incredible force. This is where nuclear fusion occurs. The sun generates its energy by turning hydrogen into helium, fusing the nuclei of hydrogen atoms together to create something new. It's the same process that powers hydrogen bombs, but here in the sun, it's controlled by the natural balance between gravity trying to crush everything inward and the pressure of all that heat and energy pushing outward. It's a delicate equilibrium that's been maintained for billions of years. The scale of this fusion process is staggering. Every single second, the sun fuses 600 million tons of hydrogen. 600 million tons. Every second. Day after day, year after year, for billions of years. It's a number so large it almost loses meaning, but try to picture it. 600 million tons of the lightest element, transformed into something heavier, releasing energy in the process. But here's something remarkable. When hydrogen fuses into helium, a tiny bit of mass goes missing. It doesn't just vanish. Instead, it's converted into pure energy following Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. Every second, 4 million tons of matter are converted into pure energy. 4 million tons simply cease to exist as matter and become the light and heat that eventually reaches us here on Earth. The total power output of the sun is truly astronomical. Its luminosity, the total amount of energy it radiates in all directions, is 3.8 times 10 to the 26th watts. That's a 3 followed by 26 zeros. In more familiar terms, it's about 386 billion megawatts. The sun produces more energy in 1 second than humanity has used in our entire history. This fusion process produces something fascinating called neutrinos. These are tiny, almost massless particles that barely interact with ordinary matter. They're created in vast numbers during fusion, and they stream out from the core in all directions. For many years, scientists detected fewer neutrinos coming from the sun than their calculations predicted. This was called the solar neutrino problem, and it was a genuine mystery. Eventually, we discovered that neutrinos can change their type as they travel, transforming from one kind into another. This helped us understand fundamental physics in new ways, and the sun was our laboratory. Now, when energy is created in the core through fusion, you might think it would quickly escape and travel out into space. But the journey of that energy is incredibly long and complicated. A photon of light created in the core doesn't just zip straight out. Instead, it can take anywhere from 100,000 to 200,000 years for that photon to make its way from the center to the surface. 100,000 years. Think about that. Light created in the sun's core before humans built the first civilizations is only now reaching the surface and beginning its 8-minute journey to Earth. Why does it take so long? Because the sun is incredibly dense in its interior, and light doesn't travel in a straight line. Instead, it bounces around, absorbed and re-emitted countless times, traveling in a random walk through the layers of the sun. The first major layer outside the core is called the radiative zone. Here, energy moves outward primarily through radiation. Photons bounce from atom to atom, scattered this way and that, gradually working their way outward through this dense plasma. The journey through this zone alone can take thousands of years. Then there's a fascinating region called the tachocline. This is a thin boundary layer between the radiative zone and the next layer outward. Scientists believe this is where the sun's powerful magnetic field is likely born, generated by the interaction between different layers of the sun rotating at different speeds. It's a place where the character of the sun fundamentally changes. Beyond the tachocline lies the convective zone. Here, the method of energy transport changes dramatically. Instead of radiation bouncing around, heat moves through convection, just like water boiling in a pot or the wax rising and falling in a lava lamp. Hot plasma rises toward the surface, cools, and then sinks back down, creating enormous circulating currents that carry heat outward. When this hot plasma reaches the surface, we can actually see the evidence of these convection cells. They're called granules and they look like bubbles on the sun's surface. Each granule is about the size of Texas or larger. Imagine that. A single convection cell, one bubble in this cosmic lava lamp, larger than an entire state. They appear as bright centers where hot plasma is rising, surrounded by darker edges where cooled plasma sinks back down. And here's a curious thought. If space had air to carry sound waves, how loud would the sun be? Scientists have calculated that if we could hear the sun from Earth, it would produce a constant roar of about 100 decibels. That's as loud as a rock concert or a chainsaw. A constant, unending wall of sound, the roar of fusion and convection and plasma churning in that great sphere 93 million miles away. Fortunately for our ears and our sanity, space is a vacuum, and that cosmic symphony stays silent. So this is the engine that powers our star. The crushing core where hydrogen becomes helium. The radiative zone where light wanders for millennia. The tachocline where magnetism is born. The convective zone where plasma churns and rises. And finally, those Texas-sized bubbles at the surface where all that energy finally prepares to leap into space and begin its journey to us. Now let's talk about what we can actually see. The face of the sun. The part that greets us each morning and bids us farewell each evening. The visible surface of the sun is called the photosphere. This is the layer we're looking at when we see the sun in the sky. It's not a solid surface, of course. Remember, there is no solid surface on the sun, but it's the layer where the plasma becomes thin enough that light can escape into space. It's where the sun becomes visible, where photons finally complete their 100,000-year journey from the core and leap out into the cosmos. The temperature of the photosphere is around 5,500 degrees Celsius. Now that's still incredibly hot. It would vaporize any material we know of instantly. But compared to the 15 million degrees at the core, it's actually quite cool. It's fascinating, isn't it? A place so hot it defies our everyday experience, and yet we call it cool because of the even more extreme conditions deeper inside. Here's something that surprises many people. From space, the sun is actually white. Pure white. Not yellow, not orange, but white. We think of the sun as yellow because that's how it appears to us here on Earth, but that's an illusion created by our atmosphere. Earth's atmosphere scatters light, and it scatters blue light more than other colors. That's why the sky appears blue during the day. All that blue light is being scattered in every direction. When we look at the sun through our atmosphere, some of that blue light has been scattered away, leaving the sun looking more yellow or orange, especially when it's near the horizon and the light has to travel through more atmosphere to reach our eyes. But to an astronaut in space looking at the sun without the filtering effect of air, the sun appears as a brilliant white sphere. The sun emits light across a broad spectrum of wavelengths, but it emits the most energy in the green-blue part of the spectrum. Our eyes have evolved to be most sensitive to exactly this range of wavelengths, which makes perfect sense. We evolved under this sun, so naturally our vision is optimized for the kind of light our star produces most abundantly. Astronomers measure the brightness of stars using something called magnitude. The absolute magnitude of the sun, which is how bright it would appear if it were placed at a standard distance of 32.6 light-years away, is plus 4.83. That might not sound particularly impressive, and in the grand scheme of stars, it isn't. There are stars far more luminous than our sun. But the sun doesn't need to be the brightest star in the galaxy. It just needs to be ours. From Earth, the sun's apparent magnitude, how bright it actually appears to us here, is minus 26.74. The magnitude scale is a bit counterintuitive. Lower numbers mean brighter objects, and negative numbers are very bright indeed. The sun, from our perspective, is by far the brightest object in our sky. Nothing else even comes close. The sun doesn't just emit visible light. It emits radiation across a vast range of the electromagnetic spectrum. On one end, there's ultraviolet light. The sun produces UVA, UVB, and UVC radiation. These are the high-energy photons that can damage our skin and cause sunburns. Fortunately, our atmosphere blocks most of the most dangerous UVC radiation. UVB is partially blocked and UVA mostly makes it through. This is why we need sunscreen, why we can get sunburned even on cloudy days. That ultraviolet radiation is always there, streaming down from the sun. On the other end of the spectrum, the sun emits infrared radiation. This is heat. Pure radiant heat. In fact, about half of all the energy reaching Earth from the sun is in the form of infrared light. You can't see it, but you can certainly feel it. Step from shade into sunlight and that warmth on your skin, that's infrared radiation from the sun, absorbed by your body and converted into heat. Even further along the spectrum, in the most energetic regions, the sun's outer atmosphere, a layer we'll talk more about later called the corona, emits X-rays. These are highly energetic photons that would be quite dangerous to us, but fortunately our atmosphere blocks them completely. They never reach the surface. Our planet's protective blanket of air shields us from so much. There's a measurement called the solar constant, which tells us how much solar power reaches the top of Earth's atmosphere. It's approximately 1,361 watts per square meter. Picture a square meter about the size of a small coffee table. At the top of our atmosphere, directly facing the sun, that square meter receives 1,361 watts of power. That's the raw energy output of our star, spread across the vast distance between the sun and Earth, still strong enough to light our days and warm our world. Not all of that energy makes it to the ground, of course. Our atmosphere reflects some of it back into space. Some is absorbed by clouds, by water vapor, by the air itself. But enough gets through. Enough to drive our weather, to power the growth of every plant, to sustain the great cycles of life that make our planet so remarkable. This is the face of the sun we know. The photosphere glowing white in space, appearing yellow through our sky. The visible light that lets us see the world around us. The ultraviolet that we must protect ourselves from. The infrared warmth that makes a sunny day feel so pleasant. And the X-rays safely blocked above our heads. All of it streaming out constantly, reliably, day after day, the gift of light and heat from our star. The sun is not a calm, peaceful sphere of light. It's dynamic, violent, magnetic, and constantly changing. There's a wild side to our star that reveals itself when we look beyond the bright surface we see each day. Just above the photosphere lies a thin layer called the chromosphere. It's only a few thousand kilometers thick, which on the scale of the sun is incredibly thin, like the skin of an apple. This layer has a beautiful reddish color, though we can't usually see it because it's overwhelmed by the bright light of the photosphere beneath it. But during a total solar eclipse, when the moon blocks the photosphere, the chromosphere can be glimpsed as a thin reddish ring around the edge of the sun. Beyond the chromosphere is something called the transition region. This is an extraordinarily thin layer, sometimes just a few hundred kilometers thick, where something very strange happens. The temperature suddenly spikes. Dramatically. It's one of the great mysteries of solar physics. Because above the transition region lies the corona, the sun's outer atmosphere. This is the wispy ethereal halo of light that extends millions of kilometers into space. During a total solar eclipse, when the moon covers the bright disk of the sun, the corona becomes visible as a shimmering, ghostly crown around the darkness. It's one of the most beautiful sights in nature, and people have traveled to the ends of the earth for just a few minutes of viewing it. But here's the mystery. The corona is hot. Incredibly hot. Its temperature reaches about 2 million degrees Celsius. Let that sink in for a moment. The surface of the sun is 5,500 degrees. As you move away from the sun, you'd expect things to get cooler, just like moving away from a campfire. But instead, the temperature increases. Dramatically. The corona is hundreds of times hotter than the surface below it. For decades, scientists have puzzled over this. How does the outer atmosphere get so much hotter than the surface? It seems to violate our basic intuitions about heat. The leading theories involve magnetic fields and waves of energy, but this coronal heating problem remains one of the fascinating unsolved mysteries of solar science. The sun is a magnetic creature. Its powerful magnetic field shapes and controls much of what happens in its atmosphere. And this magnetic field isn't static. It changes, it shifts, it evolves over time. Every 11 years, something remarkable happens. The sun's magnetic field completely reverses. The north magnetic pole becomes the south pole, and the south becomes the north. The entire field flips. On Earth, our magnetic field is relatively stable, though it has reversed many times over geological history. But the sun does it like clockwork every 11 years, as regular as the sun itself. This magnetic reversal is part of what we call the solar cycle. Over this 11-year period, the sun's activity waxes and wanes, rising and falling in a predictable rhythm. During times of high activity, the sun is covered in sunspots and frequently unleashes flares and eruptions. During quiet times, the surface can be almost entirely clear. Sunspots are one of the most visible signs of the sun's magnetic activity. These are dark patches on the photosphere, regions where powerful magnetic fields have burst through the surface. The magnetic field in a sunspot is so strong that it suppresses the convection of heat from below, making the region cooler than its surroundings. Now, cooler is relative. A sunspot is still around 4,000 degrees Celsius, hot enough to vaporize anything we know of. But compared to the surrounding 5,500 degree surface, they appear dark, like bruises on the face of the sun. At solar maximum, the peak of the 11-year cycle, the sun can be covered with dozens or even hundreds of sunspots. The surface looks mottled and active like a bubbling pot. The magnetic field is complex and tangled, creating conditions ripe for dramatic events. At solar minimum, the quietest part of the cycle, weeks or even months can go by without a single sunspot appearing. The sun looks calm, serene, almost peaceful. But even at solar minimum, the sun is never truly quiet. It's just a matter of degree. The magnetic fields that create sunspots can also cause solar flares. These are sudden, massive explosions of radiation. In just a few minutes, a region of the sun can brighten dramatically, releasing as much energy as billions of nuclear bombs. The radiation from a flare, traveling at the speed of light, reaches Earth in just 8 minutes. When a major flare erupts on the side of the sun facing Earth, it can disrupt radio communications, damage satellites, and create beautiful auroras in our upper atmosphere. Sometimes, magnetic fields on the sun arch up from the surface, creating gigantic loops of glowing plasma. These are called prominences. They can be enormous, dwarfing the size of Earth many times over. Some prominences are relatively stable, lasting for days or even weeks, hanging above the surface like glowing bridges anchored at both ends. Others are more dynamic, twisting and writhing as the magnetic field shifts beneath them. And then there are coronal mass ejections, or CMEs. These are perhaps the most dramatic events the Sun produces. A CME is a huge bubble of plasma, sometimes containing billions of tons of material, hurled into space at speeds that can exceed 1,000,000 miles per hour. When a CME erupts, it tears away from the Sun, carrying tangled magnetic fields with it, expanding as it travels through space. If a CME happens to be aimed at Earth, and if it's powerful enough, the results can be significant. When it arrives, typically 1 to 3 days after leaving the Sun, it slams into Earth's magnetic field, compressing it, distorting it. This can cause geomagnetic storms that create spectacular auroras, but can also induce electrical currents in power grids and pipelines, potentially causing blackouts and damage to infrastructure. In 1859, a massive CME called the Carrington event caused auroras visible as far south as the Caribbean and reportedly set telegraph systems on fire. If a similar event happened today in our technologically dependent world, the consequences could be severe. The Sun's gravity at its surface is also worth noting. It's 28 times stronger than Earth's gravity. If you could somehow stand on the Sun's surface, and if you weighed 150 pounds on Earth, you would weigh 4,200 pounds on the Sun. Of course, you'd be vaporized long before the gravity became a problem, but it illustrates just how massive the Sun truly is. So this is the wild side of the Sun. The magnetic beast that reverses its poles every 11 years. The source of flares and eruptions and vast bubbles of plasma hurled into space. The star whose outer atmosphere burns hundreds of times hotter than its surface for reasons we're still trying to fully understand. It's not just a steady lamp in the sky. It's dynamic, active, powerful, and occasionally dangerous. And it's this complex, magnetic, ever-changing nature that makes the Sun such an endlessly fascinating subject of study. The Sun's influence doesn't end at its visible edge. It reaches out across the solar system, filling the space between the planets with its presence. This is the realm of the solar wind. The solar wind is a constant stream of charged particles, primarily protons and electrons, flowing away from the Sun in all directions. It pours out from the corona, that superheated outer atmosphere, accelerating as it moves into space. The Sun is constantly exhaling, breathing out this invisible wind that fills our solar system. This wind moves fast, incredibly fast. On average, it travels at about 1,000,000 miles per hour. That's fast enough to cross the distance from the Sun to Earth in just a few days. Some streams of solar wind move even faster, racing through space at speeds that can reach 2 or 3 million miles per hour when driven by explosive events on the Sun. The solar wind represents a genuine loss of mass for the Sun. Every single second, the Sun loses about 1.5 million tons of material to this wind. 1.5 million tons every second, carried away into space, never to return. Now that sounds like a lot, and it is. But remember the scale of the Sun. It's so massive that even losing 1.5 million tons per second, it would take trillions of years to significantly reduce the Sun's mass through the solar wind alone. It's like trying to empty an ocean with a teaspoon. This constant outflow of particles creates something remarkable. A vast magnetic bubble that surrounds our entire solar system. We call it the heliosphere. The solar wind carries the Sun's magnetic field with it as it flows outward, creating this protective cocoon that shields our solar system from the harsh environment of interstellar space. Beyond our heliosphere, there's galactic cosmic radiation, high-energy particles accelerated by supernovas and other violent events across the galaxy. The heliosphere deflects much of this radiation, protecting the planets within, including Earth. The heliosphere extends far beyond the planets, far beyond Neptune and Pluto, out into the distant reaches where the solar wind finally encounters the pressure of interstellar space and comes to a stop. This boundary, where the solar wind meets the thin gas between the stars, is called the heliopause. It marks the edge of the Sun's domain, the boundary between the solar system and the galaxy beyond. The Voyager spacecraft, launched in the 1970s, have actually crossed this boundary. Voyager 1 reached the heliopause in 2012, and Voyager 2 followed in 2018. They're now traveling through interstellar space, the first human-made objects to leave the sun's protective bubble, sending back data from beyond the edge of our cosmic neighborhood. When the solar wind reaches Earth, it encounters our planet's magnetic field. Most of the time, our magnetosphere deflects the solar wind around us, like a rock in a stream diverting the water. But some particles get funneled down along our magnetic field lines toward the poles. When these charged particles slam into the upper atmosphere near the north and south poles, they excite atoms of oxygen and nitrogen, causing them to glow. This creates the auroras. The northern lights, the aurora borealis, and its southern counterpart, the aurora australis. Shimmering curtains of green and red and purple dancing across the night sky, a visible manifestation of the sun's invisible wind interacting with our world. The interaction between the sun and Earth isn't always so beautiful. Solar activity can create what we call space weather, and sometimes that weather can be stormy. When a powerful solar flare erupts or a coronal mass ejection slams into Earth's magnetic field, it can cause geomagnetic storms. These can disrupt GPS signals, interfere with radio communications, induce electrical currents in long power lines and pipelines, and in extreme cases, damage satellites or even cause power grid failures. The most extreme solar storm in recorded history occurred in 1859. It's known as the Carrington event, named after the astronomer Richard Carrington who observed the solar flare that caused it. When the coronal mass ejection from this event hit Earth, it created geomagnetic disturbances so powerful that auroras were seen as far south as the Caribbean and Hawaii. Telegraph systems, the high technology of the day, went haywire. Telegraph operators reported sparks flying from their equipment, paper catching fire, and some telegraph systems continued to work even after being disconnected from their batteries, powered solely by the electrical currents induced by the magnetic storm. If an event of similar magnitude happened today with our dependence on satellites, GPS, and vast interconnected power grids, the potential damage is difficult to fully estimate. The sun affects more than just the planets. There are comets that venture so close to the sun they actually graze through its atmosphere. These are called sun-grazing comets, and many of them are doomed. As they swing around the sun, passing through the corona, the intense heat can vaporize them completely. We've observed thousands of these comets, many discovered in images taken by sun-observing satellites. Some survive their close passage, emerging on the other side. Others simply vanish, torn apart and vaporized by their proximity to our star. Humanity has sent spacecraft to study the sun up close. The Parker Solar Probe, a NASA mission launched in 2018, is doing something extraordinary. It's diving into the sun's outer atmosphere, into the corona itself, becoming the first spacecraft to actually touch the sun protected by a revolutionary heat shield that can withstand temperatures of over 2,500 degrees Fahrenheit. Parker is sending back data from closer to the sun than any previous spacecraft, helping us understand the mysteries of coronal heating and the origins of the solar wind. Another spacecraft, called SOHO, the Solar and Heliospheric Observatory, has been watching the sun continuously since 1995. Positioned at a special point in space where the gravity of Earth and Sun balance, SOHO has given us an uninterrupted view of our star for nearly 3 decades. It has revolutionized our understanding of the sun's interior, tracked countless solar storms, and discovered over 4,000 comets. It's been our faithful sentinel, keeping watch over the sun day after day, year after year. So the sun's reach extends far beyond its visible surface. It fills the solar system with its wind, creates a protective bubble around all the planets, paints auroras in our skies, and occasionally reminds us of its power with storms that can affect our technology. The sun doesn't just shine on us from a distance. It touches us constantly, invisibly, through the solar wind that flows past our world every moment of every day. Now let's talk about the relationship between the sun and our home. The bond between our star and our planet that makes everything possible. The sun sits, on average, 93 million miles away from Earth. 93 million miles. It's a distance so vast it's hard to truly comprehend. If you could drive a car at highway speeds toward the sun, never stopping, never slowing down, it would take you over 170 years to get there. And yet, on the scale of the universe, on the scale of the distances between stars, this is remarkably close. The sun is our neighbor, our companion, near enough to warm us but far enough not to destroy us. Light travels faster than anything else in the universe, racing through space at 186,000 miles per second. And yet even at this incredible speed, light from the sun takes 8 minutes and 20 seconds to reach Earth. When you step outside and feel the sunlight on your face, you're feeling light that left the sun more than 8 minutes ago. You're experiencing the sun not as it is right now, but as it was in the very recent past. If the sun were to suddenly vanish, we wouldn't know for 8 minutes and 20 seconds. The sky would remain bright, the world would stay warm, and then suddenly the light would go out. Earth's orbit around the sun isn't a perfect circle. It's slightly elliptical, which means our distance from the sun changes throughout the year. In early January we reach perihelion, the point where we're closest to the sun. We're about 91 million miles away at this time. In early July we reach aphelion, our farthest point, about 94.5 million miles away. The difference is about 3 million miles. Now, you might think that being closer to the sun in January would make it warmer, and being farther in July would make it cooler. But for those of us in the northern hemisphere, January is winter and July is summer. This tells us something important. Our seasons are not caused by our distance from the sun. They're caused by Earth's tilt. Our planet is tilted on its axis by about 23.5 degrees. As we orbit the sun, this tilt means that different parts of Earth receive more direct sunlight at different times of year. In June, the northern hemisphere is tilted toward the sun, receiving more direct rays, creating summer. The southern hemisphere is tilted away, receiving less direct sunlight, experiencing winter. 6 months later, the situation is reversed. It's the angle of the sunlight, not the distance to the sun, that creates the seasons we experience. One of the most spectacular demonstrations of the Sun-Earth relationship is a total solar eclipse. These occur when the moon passes directly between Earth and the sun, blocking the sun's light and casting a shadow on our planet. What's remarkable is how perfectly matched the sizes and distances are. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This cosmic coincidence means that from our perspective here on Earth, the sun and moon appear to be almost exactly the same size in the sky. The moon can just barely cover the entire disk of the sun, creating those breathtaking moments of totality when the corona becomes visible. It's a perfect alignment that won't last forever. The moon is slowly drifting away from Earth, and millions of years from now, total solar eclipses will no longer be possible. We live in a special time when this celestial coincidence is possible. The sun is the ultimate source of energy for almost all life on Earth. Through the process of photosynthesis, plants capture sunlight and use it to convert carbon dioxide and water into glucose and oxygen. This is the foundation of nearly every food chain on our planet. Plants grow using the sun's energy. Animals eat the plants. Other animals eat those animals. The energy flowing through every ecosystem, powering every living thing, ultimately came from the sun. Even the fossil fuels we burn, oil and coal and natural gas, are stored solar energy, the remains of ancient life that grew using sunlight millions of years ago. The sun affects our bodies directly as well. When sunlight, specifically UVB radiation, strikes our skin, it triggers a chemical reaction that produces vitamin D. This vitamin is essential for healthy bones, immune function, and many other processes in our bodies. For most of human history, getting enough vitamin D wasn't a problem. People spent time outdoors and their skin made what they needed. It's only in our modern era, with more time spent indoors, that vitamin D deficiency has become common. The sun has been our source of this vital nutrient for as long as humans have existed. The sun even helps create the tides. We usually think of tides as being caused by the moon, and that's mostly correct. The moon's gravity is the primary force creating the rise and fall of ocean water. But the sun contributes as well. When the sun and moon align, during new and full moons, their gravitational effects add together, creating particularly high and low tides called spring tides. When they're at right angles to each other, during quarter moons, their effects partially cancel out, creating weaker tides called neap tides. The sun's gravity, even from 93 million miles away, is strong enough to pull on Earth's oceans. The sun is the primary engine driving Earth's climate and weather. Every weather pattern, every storm, every breeze, is ultimately powered by the uneven heating of Earth's surface by sunlight. The equator receives more direct sunlight than the poles, creating temperature differences. Warm air rises, cool air sinks, and the rotation of the Earth creates patterns of circulation. All the complexity of Earth's climate system, all the intricate interactions between atmosphere and ocean and land, all of it is driven by the energy we receive from the sun. Humanity hasn't always understood our relationship with the sun. For most of history, it appeared that the sun moved around the Earth, rising in the east and setting in the west. It seemed obvious that Earth was the center and everything else moved around us. But some thinkers question this. Aristarchus, a Greek astronomer who lived over 2,000 years ago, was one of the first to suggest that Earth actually orbits the sun, not the other way around. His ideas were largely ignored or rejected in his time. The notion that Earth, our solid ground beneath our feet, could be moving through space seemed absurd. It wasn't until the 1500s that Nicholas Copernicus developed a comprehensive model placing the sun at the center of the solar system. His work, published near the end of his life, sparked a revolution in how we understand the cosmos. The Copernican model, as it came to be known, showed that the movements of the planets made much more sense if they were all orbiting the sun rather than Earth. It was a profound shift in perspective. Galileo Galilei, in the early 1600s, used one of the first telescopes to observe the heavens and found evidence supporting Copernicus. He also observed sunspots, those dark patches on the sun's surface. Unfortunately, he looked at the sun without adequate protection and damaged his eyesight in the process. A reminder that the sun, giver of light and life, must also be treated with respect and caution. Throughout human history, across virtually every culture, the sun has been revered. The ancient Egyptians worshipped Ra, the sun god, depicted with the head of a falcon crowned with a solar disk. The Greeks had Helios, who drove his chariot across the sky each day, pulling the sun behind him. The Romans called the sun Sol, from which we get words like solar and solstice. The Aztecs had Tonatiuh, demanding sacrifice to ensure the sun would rise each day. The Japanese honored Amaterasu, the sun goddess. In Hinduism, Surya rides across the sky in a chariot pulled by 7 horses. In nearly every corner of the world, humans looked up at the bright disk in the sky and saw something divine, something worthy of awe, worship, gratitude. And perhaps they weren't wrong. Perhaps they understood, in their own way, something fundamental, that we owe our existence to the sun, that it is, in a very real sense, the source of all we are and all we have. Our ancient ancestors may not have understood nuclear fusion or electromagnetic radiation, but they understood dependence. They understood debt. They understood that life comes from the light and warmth of the sun. So this is our relationship with our star. 93 million miles of space separating us, but connected by light that takes just over 8 minutes to cross that gulf. Connected by the energy that powers every living thing. Connected by the warmth that makes our world habitable. Connected by gravity and climate and the very air we breathe. The sun and earth, star and planet, locked in a relationship that has endured for billions of years and will continue for billions more. The sun may appear fixed in the sky, a stationary anchor around which everything else moves. But this is an illusion. The sun is in constant motion, spinning on its axis and traveling through space on a journey that spans hundreds of millions of years. The sun rotates, but not the way Earth does. When Earth spins, it rotates as a solid body. Every part of it turns at the same rate. The equator and the poles complete one rotation in the same amount of time, 24 hours. But the sun is different. The sun is made of plasma, not solid rock, and different parts of it rotate at different speeds. This is called differential rotation. At the sun's equator, the surface completes one rotation in about 25 Earth days. 25 days for the equator to spin once around. But as you move toward the poles, the rotation slows down. At the poles themselves, it takes about 36 Earth days to complete one rotation. 36 days. The same star, but different parts of it moving at different speeds. This might seem strange, but it makes sense when you remember that the sun is fluid, not solid. There's nothing holding it together rigidly. Different latitudes can slip past each other, rotating independently. This differential rotation has profound effects on the sun's magnetic field. As the equator spins faster than the poles, magnetic field lines get stretched and twisted, wound up like rubber bands. This tangling and twisting of magnetic fields is part of what creates sunspots, solar flares, and the 11-year solar cycle. The sun's fluid nature, its ability to rotate at different speeds, is intimately connected to its magnetic behavior. But the sun's motion doesn't end with its rotation. The sun itself is moving through space, orbiting the center of our galaxy. The Milky Way is a spiral galaxy containing hundreds of billions of stars. At its center lies a supermassive black hole, millions of times more massive than the sun, around which the entire galaxy slowly rotates. The sun is just one of those hundreds of billions of stars, out in the suburbs of the galaxy, traveling in a vast orbit around the galactic core. The sun moves fast, really fast. It's traveling at about 450,000 miles per hour through the galaxy. 450,000 miles per hour. If that seems hard to visualize, imagine that in 1 second, the sun moves about 125 miles. In the time it takes you to read this sentence, the sun has traveled hundreds of miles through space, carrying Earth and all the other planets along with it. We're located about 26,000 light-years from the center of the Milky Way. 26,000 light-years. That means if you could travel at the speed of light, it would take 26,000 years to reach the galactic center from our position. We're out in one of the spiral arms in a relatively quiet, stable part of the galaxy. Not too close to the dangerous, radiation-filled center. Not too far out in the sparse outer regions. Just right. A comfortable, safe neighborhood in the cosmic city. At the sun's orbital speed of 450,000 miles per hour, you might think it would complete an orbit around the galaxy fairly quickly. But the galaxy is vast beyond comprehension. The circumference of the sun's orbit is so enormous that even at this incredible speed, it takes a very, very long time to complete one circuit. It takes approximately 230 million years for the sun to orbit the Milky Way once. 230 million years. This span of time is sometimes called a galactic year or a cosmic year. Think about what that means. The last time the sun was in its current position in the galaxy, the age of dinosaurs was just beginning. Dinosaurs ruled Earth for the entire time it took the sun to travel all the way around the galaxy and come back to where it started. The sun has only completed about 20 orbits since it formed 4.5 billion years ago. 20 trips around the galaxy in its entire lifetime. When you think about it this way, the sun becomes more than just the center of our solar system. It becomes a traveler, a wanderer tracing a great circular path through the cosmos. Earth isn't just orbiting the sun, Earth is being carried along on the sun's journey through the galaxy, like a passenger on a cosmic ship that never stops moving. The sun never returns to exactly the same place, of course. The galaxy itself is moving, rotating, evolving. The stars around us are all on their own orbits, moving at their own speeds. The sun weaves through the galaxy, sometimes passing through denser regions of the spiral arms, sometimes traveling through quieter spaces between the arms. Over hundreds of millions of years, our stellar neighbors change. Stars that were once close drift away. New stars appear in our vicinity as they follow their own galactic paths. And all of this motion, the sun's rotation, its orbit around the galaxy, is part of an even larger motion. The Milky Way itself is moving through space, falling toward a cluster of galaxies called the Virgo cluster. And that cluster is part of an even larger structure called the Laniakea supercluster. Motion within motion within motion, scales of movement and journey that stretch the imagination. But for our purposes, for our everyday lives here on Earth, the most important motion is the sun's steady orbit around the galaxy, carrying us along through space at nearly 500,000 miles per hour. We don't feel it. There's no wind in our face from our motion through the cosmos. But we're moving nonetheless. Passengers on the sun's great journey, travelers through space and time, orbiting the heart of the Milky Way on a trip that takes hundreds of millions of years to complete. So the sun is not standing still. It never has been. It spins, different parts at different speeds, twisting its magnetic field into complex shapes. And it travels, racing through the galaxy on an orbit so vast that human civilizations rise and fall in the blink of an eye compared to the time it takes to complete one revolution. The sun is a traveler, and we travel with it, through the dark and the light, through the spiral arms of our galaxy, on a journey that began before the dinosaurs and will continue long after humanity is gone. All things have a beginning and all things have an end. Even stars. Even our sun. Let's talk about the future, about what happens when the fuel runs out and the sun's long story draws to a close. Right now, the sun is in what astronomers call the main sequence. This is the longest, most stable phase of a star's life. During the main sequence, a star steadily fuses hydrogen into helium in its core, maintaining a perfect balance between the crushing force of gravity trying to squeeze it smaller and the outward pressure of heat and radiation pushing back. The sun has been in this phase for about 4.5 billion years, and it will remain here for several billion more. These are the good years, the calm years, when the sun shines steadily and reliably. The sun has used up about half of the hydrogen in its core. Half of its fuel is gone. But don't worry, there's still plenty left. The sun is in many ways middle-aged. Not young, not old, but settled into the comfortable routine of its life. But the sun is not exactly constant. It's not the same today as it was billions of years ago. The sun gets about 10% brighter every billion years. 10% might not sound like much, but over billions of years, it adds up. The sun that shone on the early Earth, on the first single-celled organisms floating in ancient oceans, was noticeably dimmer than the sun we see today. And the sun of the future will be brighter still. In about 1 billion years, the sun will be bright enough and hot enough that Earth's oceans will begin to evaporate. The water vapor will rise into the atmosphere, and much of it will be broken apart by solar radiation, with the hydrogen escaping into space. Earth will begin to lose its oceans. The climate will shift dramatically. Life as we know it will face an existential challenge. 1 billion years from now, our descendants, if they still exist, will need to find another home or find a way to survive on a world that's becoming increasingly inhospitable. But the real drama begins in about 5 billion years, when the sun exhausts the hydrogen in its core. When that happens, the core will begin to contract under gravity, heating up. Hydrogen fusion will continue in a shell around the core, but the core itself will be inert helium, not yet hot enough to fuse. As the shell burns hotter and hotter, the outer layers of the sun will expand. Dramatically, the sun will enter its red giant phase. It will swell up, growing larger and larger, its surface cooling and turning from yellow-white to red. The sun will become enormous. Its outer layers will extend beyond the orbit of Mercury, possibly beyond Venus. Mercury will almost certainly be swallowed, consumed by the expanding atmosphere of the dying sun. Venus will likely meet the same fate. Earth's fate is less certain. Some models suggest the sun's expansion will reach Earth's orbit, swallowing our planet as well. Other models suggest that as the sun loses mass during this phase, its gravitational grip on the planets will weaken, and Earth's orbit will drift outward, possibly staying just ahead of the expanding solar atmosphere. But even if Earth isn't directly consumed, it won't be a pleasant place. The intense heat from the nearby giant sun will scorch the surface, vaporizing anything that remains. Earth, if it survives, will be a scorched, lifeless cinder. Eventually, the core of the sun will heat up enough to begin fusing helium into carbon and oxygen. This ignition will happen suddenly in what's called a helium flash. For a brief moment, the core will burn incredibly hot, but then it will settle into a new equilibrium, steadily fusing helium. This will provide a temporary reprieve, a second phase of stable burning, though it won't last nearly as long as the hydrogen burning phase. As the sun nears the end of its life, it will pulsate and shed its outer layers. These layers will drift away into space, expanding outward in a beautiful, glowing shell of gas. This is called a planetary nebula, though the name is misleading. It has nothing to do with planets. Early astronomers thought these objects looked like planets through their telescopes, and the name stuck. A planetary nebula is the outer atmosphere of a dying star, enriched with heavier elements forged in the star's core, drifting into space where it may eventually become part of new stars and planets. What's left behind, at the center of this expanding nebula, is the core of the sun. It will have collapsed into an incredibly dense object about the size of Earth but containing a significant fraction of the Sun's original mass. This is called a white dwarf. It will be extraordinarily hot at first, glowing white with residual heat, but it will no longer be producing energy through fusion. It will simply be cooling off, radiating its stored heat into space. A white dwarf is dense beyond our everyday experience. A teaspoon of white dwarf material would weigh tons. The atoms are packed together as tightly as possible without collapsing into something even stranger. Electrons are pressed up against each other, and it's the pressure of these electrons, a quantum mechanical effect, that keeps the white dwarf from collapsing further. The white dwarf that was once our sun will cool slowly. Over billions of years, it will fade from white to yellow to red to brown, gradually growing dimmer and dimmer. Eventually, after an unimaginably long time, trillions of years, longer than the current age of the universe, it will cool completely. It will become a black dwarf. A cold, dark cinder, no longer emitting any light, invisible against the darkness of space. The final fate of our sun. A dark ember, a remnant, a monument to what once was. It's a sobering story, isn't it? But it's also far, far in the future. The sun has billions of years of steady shining ahead of it. Billions of years to warm worlds, to light the darkness, to make life possible. To put the sun's power in perspective, consider this. Every second, the sun releases more energy than humanity has ever used in our entire history. All the power plants, all the engines, all the fires ever lit, all the electricity ever generated, all of it combined doesn't equal what the sun produces in a single second. We are tiny creatures living on a small world, warmed by a star of almost incomprehensible power. And even though we call it the solar constant, the amount of energy Earth receives from the sun, it's not truly constant. The sun varies slightly, changing with the solar cycle, affected by sunspot activity and other complex processes. These variations are small, just tenths of a percent, but they're real. Our reliable star changes subtly, constantly. We've learned to study the sun's interior using a technique called helioseismology. Just as earthquakes create waves that travel through Earth and reveal our planet's inner structure, the sun has waves traveling through it. These are sound waves created by the churning convection and other processes. By measuring how these waves move through the sun, by analyzing their frequencies and patterns, scientists can map the invisible interior, understanding the structure and composition of regions we can never directly see. We can listen to the sun, in a sense, and hear the story of its hidden depths. And through all of this, one fact remains central, undeniable, profound. The sun is the life giver. Without the sun, Earth would be a frozen rock drifting through the darkness of space. The average temperature would be close to absolute zero. No liquid water. No atmosphere, as even our air would freeze solid. No life. Nothing but ice and rock and silence. Every breath you take, every moment you've ever experienced, every person you've ever known, every story ever told, all of it exists because the sun shines. We are, all of us, children of the sun, dependent on its light, its warmth, its steady presence in our sky. So yes, the sun will die one day. But that day is billions of years away. For now, and for countless generations to come, the sun will rise each morning and set each evening. It will shine on new days and new lives. It will continue its great journey through the galaxy, carrying us along. And we will continue to look up at it, to study it, to wonder at it, to be grateful for it. Our star, our sun, the center of our world and the source of everything we are.